Hello there, fellow learners. Welcome back to our machine learning journey. I'm your host, Bhaskar, and today we are going to deep dive into the fascinating world of K nearest neighbors algorithm. Picture this, an algorithm that can make predictions based on similarity. How cool is that? Well, in this video, we will explore the power and versatility of KNN, K nearest neighbors. It's a popular and initiative machine learning algorithm that finds its application in both classification and regression tasks. But what makes it so special? Let's find out. But before we get started, let me quickly introduce myself. I am Bhaskar, a machine learning intuitionist, and in this video, I will be your guide through the exciting realm of K nearest neighbors. All right, let's break it down into the three main sections. First, we will understand a solid understanding of KNN algorithm. Then, we will see how KNN can be used for classification and regression tasks. Finally, we will explore practical techniques for applying and improving KNN in our own projects. Section 1, Understanding KNN algorithm. So what exactly is KNN? Well, it's an algorithm that aims to classify or predict based on similarity. You see, the instances with similar features tend to belong to the same class. It's like a birds of a feather flocking together. Let's take an example. Y equal to m1 x1 plus m2 x2 plus so on. It's an equation of a line or it's a linear regression, right? We are already aware of this, where x1, x2, x3, so on are features, and m1, m2, m3, so on are coefficients, and y1, y2, y3, so on are our instances. Okay, so let's take a plot. Let's take a plot. So here, these are the data points. So this will be our y1, y2, y3 data points. This will be our x1 and this will be our y1. So this is for 2D. If it's a three-dimensional, how it will be? So we are having three features: x1, x2, x3. So basically, we can visualize only up to three dimension, right? So in this plot, y1 and y2 are two data points and are dependent on the features. So x1 is a feature and y1 is dependent on x1. Y1 and y2 are close if they are having the similar features. Let's take an example. So x equal to 1, 2, 3. If the point is here, okay, this is also 1, 2, and 3. And let's take a one more point, this point. So this point and this point are similar. That's the basic assumption. And so as you can see with our eyes, these 2 points are very close to each other. The proximity is very less. So we can say these two data points are similar instances. To determine the nearest neighbors, we introduce the concept of K. The value of K determines the number of neighbors we consider when making predictions. It's like having a group of friends who provide advice based on the experiences. That means, so if it is a plot, I said right, depend upon the proximity or similarity. So we'll try to create a decision boundary. So this is our area. So we'll try to see what points are falling under this area. These points will be our neighbors to this point, right? So this point will be our neighbors to this point. Like here in this case, we have taken a decision boundary. So, and we can also take number of closest neighbors. Like if a plot is there, if there are so this many points. So this is our main point. Let's take three closest neighbors. So that will be this point, and this point. So we will decide how many number of neighbors we need to take. Nearest neighbors. So that's nothing but the k. So k and I means k nearest neighbors. K is number of neighbors and nearest neighbors. To determine the nearest neighbors, we already introduced the value of k. But how do we find these nearest neighbors? We measure the distance between instances using matrices like Euclidean distance. It's like calculating the distance between two places on a map. In this case, we are measuring the distance between the data points. So we have 2 points y1 and y2, right? And we want to measure the distance between it. That means we want to measure distance between y1 and y2. So as per the Euclidean distance, what will it be? It will be sum of squares of features, difference of the features. Sigma x1 minus x2, x11 minus x12 whole square plus sigma x21 minus x22 whole square plus sigma x31 minus x32 whole square, and it's go on. So what are our x1 and y1? y1 equal to m1 x11 plus m2 x12 plus c. y2 equal to m11 x21 plus m22 x22 plus c. Distance between y1 and y2 is nothing but sigma x11 minus x21 whole square plus x12 minus x22 whole square. As we have two features, we get our Euclidean distance as this one. So this will be our distance. This will be our Euclidean distance. Now, here's something important. Choosing the right value of k is important. It's a delicate balance between bias and variance. Bias refers to the error introduced by approximating a real-world problem with simplified model. In the case of KNL, bias can occur when the model makes assumptions about the underlying data distribution. With KNL, the bias tends to be low because the algorithm doesn't make strong assumptions about the data. Instead, it relies on local neighborhood to make the predictions based on similarity. So what does it mean? It means that in KNL, we are not making any strong assumptions. Simply we are calculating the points based upon the data points, based upon the local neighborhood. Variance. Variance represents the sensitivity of the model to the fluctuations in the training data. High variance means the model predictions can vary significantly with different training datasets. In the case of KNL, the variance can be high, especially when using a small value of k. When k is small, the model becomes highly influenced by the specific instances in the local neighborhood, making it susceptible to the noise or outliers in the training data. So, what does that mean? So, it means in KN that variance can be high because we are calculating Euclidean distance. So, if this distance, it depends upon one feature, second feature, and so on, or features. So this can be biased. That means it can be more weighted, it can be less weighted, and because of that, the value can change, right? So, so one more thing I want to highlight is this Euclidean distance is between the two data points. So we are calculating distance between two words individually, separately. So between these two data points, we are calculating the Euclidean distance. And similarly, if we take one more point, again between these two data points, we are calculating it separately. Okay? Yes. Increasing the value of k can reduce the variance, but may increase bias. A larger K considers more neighbors, smoothing out the predictions and reducing the influence of instances. So, with increasing the K, we can reduce the variance, but bias may increase. Always remember, bias means assumptions we are making. If the model is simple, then we are having more bias. Whereas the variance means it's a variation. So if there is a lot of variation in the data, then we are having high variance. Remember, if bias increases, variance decreases. If variance increases, bias decreases. Okay? A small value k may lead to overfitting, while a large value of k may introduce underfitting. We need a sweet spot between bias and variance trade-off. Ready for next session? Let's move on to exploring KNN in classification and regression tasks. KNN in classification and regression. In classification tasks, KNN shines by determining the unknown instance class based on majority class of its k nearest neighbors. It's like taking a vote among your friends to decide on which best movies to watch. So let's take an example. You are going to a movie and you're not sure whether you have to go or not go. What will you do? You will ask your friends, assume five friends, and who have already watched the movie, and they will give you a review. It can be good, not good. Only two values. If majority says good, then we'll go for a movie. So that's nothing but our KNR classification task. So that means we're having a point, we're taking neighbors, five neighbors, based upon majority one or zero. One, one, one. So majority is one. So it's positive. Okay. Now imagine drawing boundaries to separate different classes. These decision boundaries are formed based on the majority vote of neighbors' instances. It's like drawing lines on a map to mark the different territories. Let's not forget the exciting applications. KNN can be applied to a wide range of classification problems like image classification or sentiment analysis. It's like teaching a computer to recognize objects or to understand emotions. Amazing, right? Example. For sentiment analysis, what we usually do is sentiment analysis has a text. Hi, this is Bhaskar. So what will we do in the sentiment analysis? You want to predict the sentiment of this text. It can be either 1 or 0. 1 means positive sentiment, 0 means negative sentiment. It can also be neutral. Let's leave it for some other day. So we are having two sentiments, 0 or 1, negative or positive. So how will we calculate? How can we use KNL? Well, the first thing we have to do is, as I said previously, computer can only understand numbers, not text or characters. We need to convert into numbers. So we use pre-processing and convert into numbers. So from the text, we are calculating the features. Once we get the features, we will apply our model and get the output, either 1 or 0. So let's assume for this text we got features x1, x2, x3, and so on up to xn. So these are our features for our text. We will be predicting either 1 or 0. How will you predicting? This is one instance. You have to take one more instance. Let's take x11, x21, x31, so on, xn1. So this will be our y2. Simply use Euclidean distance between y1 and y2. After doing Euclidean distance between y1 and y2, you will get the distance, right? You will do it between y1 and y3 also. Similarly, y1 and y4, and so on. y2, y3, y2, y4. Like this, we take all possible combinations, and whichever is our k neighbors, we will take those observations and whatever it predicts. If it's a classification, it will be majority vote. If it's a regression, what will you do? It will be an aggregate. Aggregate means if you have points like 2, 2.5, and 3, these are our nearest neighbor outputs. So what will be our output? It's simply average. This will be k nearest neighbor output for a regression. In the previous example, we will get either 1 or 0 depending upon maximum voting. But KNN does not stop there. It's placing a crucial role in regression tasks also. As I said, in regression, we're simply taking the average. In our example, what can be the regression output? It's like getting an average rating from your friends to predict how much you enjoy a movie. That means on a scale of 1 to 5, someone says 4.5, and someone say 4, and someone say 5. Take the average of it. So for regression, aggregate each feature's value with similar feature value of their neighbors. So here is a cherry on the top, real life example. Think about predicting housing prices or forecasting stock market trends using KLN. The possibilities are endless. Exciting stuff, isn't it? Now, let's move on to the final session where we explore techniques for applying and improving KNN. Applying and improving KNN. Like any algorithm, KNN has its strengths and limitations. It's like simple, interpretable, effective with small data sets. However, it can be computationally complex and sensitive to feature scaling. To enhance KNN performance, we can use data preprocessing and normalization techniques. It's like preparing ingredients before cooking a delicious meal, cleaning, chopping, and seasoning. We normalize the features, otherwise, Y is bias towards more coefficient features. So, let's take an example. We have features x1, x2, and x3. We have to normalize x1 and x2 and x3. That means convert them in the range of 0 to 1, or we can also choose standardization, some other techniques also. So basically, it's simply converting into the some common range. Okay. So in normalization, we're converting into the range of 0 to 1, x1 sigma, x2 also 0 to 1, and x3 also 0 to 1. Why do you need it? Well, if we don't do it, what happens? Let's take this one. So this is our Euclidean distance, right? KLM. So if this one is more, so if you don't normalize, this value will be high, this value will be low. Let's assume is also low. That means the entire algorithm is biased towards this value. And we will get biased results. It's not good. So we need to normalize. But what about categorical features and missing values? For categorical, convert them into numbers. Whereas for missing values, we can use missing value imputation techniques like mean, medium, or mode. Whereas in practice, we may use some advanced techniques like smooth or other advanced techniques like forward fill or backward fill. What is forward fill? If we have values like 1, 2, 3, missing 4, 5. Forward will impute this value with 3. What about backward fill? For similar example, we are going in the backward direction. This value will be imputed with 4. So this is forward fill, F fill, and this is backward fill, B fill. Mostly we're using this for time series data. Feature selection and dimensionality reduction also plays a vital role in KNN effective lens. It's like declustering your living space to separate or create a better environment, keeping what's important and removing what's not. Choosing the right decision metrics is another crucial aspect. Different characteristics of the data may require different metrics. It's like using different tools for different tasks. Before we wrap up, let's touch upon some advanced variants of KNN, such as weighted KNN or distance weighted KNN. These variants offer additional flexibility and customization to fit specific scenarios. In standard KNN algorithm, each neighbor contributes equally to the final prediction. However, in the weighted kernel, the influence of each neighbor is adjusted by assigning weights. The closer a neighbor is to the query point, the higher is the weight, indicating that it has stronger influence on prediction. So, what is weighted kernel? If you take an example, so this one we are multiplying with some weights. That's it. This is our weighted kernel. Simple, isn't it? So let's go to the assumptions of KNN. Assumption number one, similarity assumption. The KNN algorithm assumes that instances with similar feature values tends to belong to the same class or having similar target values. That means we are having similarity of features. If we have similar features, that means they are close. That means in the plot, if these two features are similar, then they are closer. That's assumption number one. Assumption number two, feature relevance assumption. Algorithm assumes that all features used for classification or regression are relevant and contribute to the similarity calculation. That means whatever we are features we are having, x4, x2, x3, so on, they should be relevant and they should contribute to our y prediction. Assumption 3, local decision boundary assumption. KNN assumes that decision boundary between the different classes are locally defined based on the distribution of training instances. It assumes that decision boundary can vary across different regions of feature space. What does it mean? So, KNN assumes that decision boundaries are locally defined. That means depending upon our data points, we can define decision boundaries. Next assumption, uniform distribution assumption. The algorithm assumes that training data represents a reasonably uniform distribution of instances across feature space. That means if this is your feature space, you should have uniform kind of distribution. That is this assumption. Next assumption, independence assumption. KNN assumes that features used for classification or regression are independent of each other. This assumption implies that correlation or dependence between the features is not explicitly taken into account by algorithm. That means if you have features x1, x2, so on, they should be independent of each other. That means x1 is independent of x2 and x2 is independent of x3. They are not dependent. That's what his assumption is. Next assumption, adequate training data assumption. The algorithm assumes that the training data is representative of the population or problem domain. That means if this is our population, this is our sample, this sample is representative of the population. That means sample representative of the population. Okay, that is this assumption. It is essential to assess these assumptions in the context of your specific data sets and problem before applying KNL. Understanding the underlying assumptions helps in selecting the appropriate pre-processing techniques, feature selection, and determining the sustainability and suitability of the algorithm for your particular task. We covered a lot of ground today. Let's quickly recap the key points we explored in this video. Conclusion. Today, we dive into a fascinating world of k-nearest neighbors. We understand its algorithm, explore its applications in classification and regression, and learn techniques to apply and improve its performance. I encourage you to experiment with KNN in your own machine learning projects. It's versatile and powerful algorithm that can offer unique insights and predictions. Keep exploring and pushing the boundaries of what's possible. If you want to dive even deeper into the world of machine learning, don't forget to check out the other videos in our machine learning mastery playlist. We cover more advanced algorithms and techniques that will take your skills to the next level. Before we go, I want to express my heartfelt gratitude for your time and enthusiasm. Remember, learning is a journey, and we are all in this together. Keep that passion burning and never stop exploring the exciting world of machine learning. If you enjoyed this video and found it useful and helpful, please give it a thumbs up, subscribe to our channel, and share it with others who might find it interesting. Your support means the world to us. Thanks again for joining me today. Until the next time, happy learning.